Okay, so let's start here with this question. Which radical is the least stable? All right, which radical is going to be the least stable here? First of all, could anybody tell me which one of these radicals is going to be the most stable radical? There's one that's by far more stable than any of the others. It's going to be C, isn't it, right? It's definitely going to be C, and that's because it is allylic, yes. So we'll put here C is most stable, right? And we could write the resonance contributor for that if we wanted to. Okay, I'll just put the curved arrows in like this, and then we could draw the resonance contributor, which is going to look something like this. All right, like that. But there's one of these that is by far the least stable. Could anybody tell me which one of these is the least stable by a long shot? Yeah, it's B, big time, right? This one is going to be least stable. And the reason why is because this is vinylic. We know that vinylic radicals have we have a very high bond dissociation energy to form a vinylic radical. Okay, good. Let's move on from there. It says, which species represents an intermediate during the reaction shown below? So we're taking propane. And we're treating that with chlorine and light, and we're doing a halogenation, right? This is nothing more than a halogenation reaction, just a substitution reaction. So if we're using chlorine and light, which one of these looks like the most reasonable intermediate? Can anybody tell me the answer to number 2? It's going to be A, isn't it, right? It's going to be A, because if we're using chlorine and light, this means this is a radical mechanism, right? So it can't be a carbocation, it can't be a carbanion, and the alkene has nothing to do with it. And so the answer would be the radical, right? You do the hydrogen abstraction, you form the radical, then you do a halogen abstraction, and you get your 2-chloropropane. All right, let's move on from there. I think that this was one of the questions in the quiz, maybe, is which is a propagation step in the free radical chlorination of ethane. So the free radical chlorination of ethane is where we take ethane, and we combine it with chlorine. And of course, we put that in light, and we end up with chloroethane, like this, plus we end up with HCl. So propagation steps. So remember, we have initiation and then we have propagation. Well, the two propagation steps are first going to be a hydrogen abstraction, right? And then we have the halogen abstraction. So I'll just put here chlorine, since chlorine is the halogen we're using abstraction. So which one of these looks the most like the correct step here? So the first one, we have a radical plus ethane gives us another ethane and another radical. So it can't be this one. This one will be a termination step, isn't it? Termination, because we have two radicals coming together and they annihilate each other. The next one is the same thing. This must be a termination step. So I'll just put here termination. But in D, we have a halogen abstraction, don't we? So we're taking our ethane radical, we're combining it with the chlorine, and we end up removing the chlorine. So this is the, we'll put here halogen abstraction, right? So this is the second part of propagation. So the correct answer is D. All right, continuing on in the vein of chapter 10. So could anybody tell me in this reaction, number 4, is this a Markovnikov or an anti-Markovnikov addition? Or is it not pertinent in this case? It's neither, right? It's not pertinent in this case. There's no Markovnikov and anti-Markovnikov, is there, right? Because we have one hydrogen on each of the double bonded carbons, and so there's no Markovnikov or anti-Markovnikov. But that doesn't mean we can't do a reaction with HBr and peroxides. So if you remember that the reason we get anti-Markovnikov addition, and it doesn't matter in this case, is because when we form the bromine radical, right, it ends up adding to the double bond. So we're going to do something that looks like this, where we add the bromine, and then we're going to form the radical. And so the only one that makes sense here is A. And even if you weren't completely sure of the mechanism, you can be sure that C is wrong because that's a carbanion, and D is wrong because that's a carbocation, and B is wrong because we haven't added a halogen in the reaction. So there we go. All right, let's move on to number 5. Number 5 is another one I think was on the quiz. So what's the expected product? Well, there's 2 benzylic positions on this molecule. You have a benzylic position here, and then you have a benzylic position here, but the one in blue is more substituted. So that's the one where the bromine is going to go. And so the answer would be C. So benzylic bromination, so I won't spend too much time on that one. All right, question number 6. Which reaction gives an efficient synthesis of 1-bromo-2-methylpropane? So if we wanted to make this molecule, if we look at the first one, if we're doing bromination, the bromine is going to be added at the most substituted carbon, and so it can't be A. If we look at the next one, you can do this reaction with HBr. The only problem here is that you're going to end up forming a tertiary carbocation, right? After you convert this into a good leaving group, okay, you're going to end up doing a hydrogen shift or a hydride shift as the leaving group leaves to give you a tertiary carbocation. What about C? Is C going to give you the correct product? Yes or no? Could anybody tell me, would C give you the correct product? Absolutely, right? This is an anti-Markovnikov addition. And so C would give you the correct product. Good. All right, D is just plain wrong because that's a dibromination. You add 2 bromines in an anti-fashion. So let's move on from there. This one here, number 7, which reaction coordinate diagram represents the reaction shown in which radical Y is very non-regioselective? So if it's non-regioselective, that means, is it going to have a high activation energy or a low activation energy? If it's non-regioselective. Yeah, it should have a low activation energy, right? Because if it's non-regioselective, based on the Hammond postulate, if this is your intermediate where I have the little blue dot, it's going to look mostly like the starting material, right? If you look at all the other ones, you can see that the intermediate is pretty far away in energy from the starting material. You see here it's very close in energy to the intermediate here, your transition state. Here you see the transition state looks mostly like the products. And here you see the transition state looks a little bit more like the reactants, but it has a really high activation energy. So in B, it's got a low activation energy and the transition state is going to mostly look like the reactants. And so this is the one that is going to be the most non-regioselective. It's going to be B. So we went over that quite a bit in chapter 10. So if you need to review that, go back and take a look at that. Let's see here. Number 8, which alkane-alkene pair would be formed by a disproportionation reaction? We didn't cover this, so I'll skip that one. Number 9, I think this was a question on the practice quiz, so I'll go over this one very quickly. If we were to do a polymerization on vinyl chloride and vinylidene chloride, well, it's going to have vinyl chloride and vinylidene chloride pieces in it. Did anybody get this one? Number 9? Which one would be the best answer here? So this portion is going to come from the vinyl chloride. Okay, this one here comes from the vinyl chloride. And then this portion here is going to come from the vinylidene chloride. So remember, it's an alternating polymer, Saran. You have vinyl chloride, vinylidene chloride. Right, so you want to add them together in the way that they're written. Right, so you would start like with the vinyl chloride, right? You'd say CH2, right? Like this, and then you'd say CHCl, and then you'd go over to the vinylidene chloride, so you'd say CH2, and then Cl2, like that. So that's what is written in B. Just give me a thumbs up if that makes some sense to you now that you see it. So that would be the repeating unit in Saran. This repeating unit here. All right, good. Let me just move this. No, that's not going to work, is it? Okay, let's move on to number 10. At which of the indicated positions would the bromine radical react at the fastest rate? Could anybody answer this one? Where's the bromine radical going to react the fastest? If you did it, it's going to be at position 2, right? Why, Audrey? Because it's a benzylic position, right? So this is benzylic position. So this is going to be the answer is number 2. Which position would it react the slowest? Can anybody tell me that? Yeah, it's going to be number 1. Number 1 is vinylic position. Good. All right. I'm going to skip number 11. What's the product that's formed in number 12? So this is, again, a polymer question. So again, you do the same thing. So you start with a CH2, you remove the double bond, you have a single bond, and then you have CHCN, and that's your repeating unit. That's all there is to it. You're just going to repeat this over and over and over. And so the correct answer is going to be B. Okay, let's take a look at some redox chemistry here. Question number 1 is, which reagents are the best for carrying out this reaction? So we have a ketone and we have an ester. We only want to reduce the ketone. We don't want to reduce the ester. So does anybody have any ideas about this one? Yeah, somebody says A. So that's a sodium borohydride reduction. Yeah, because sodium borohydride is weaker. But in the sodium borohydride reduction, I don't remember us using H3O plus, and that we only did it with water as a solvent. So if we go back here, it says, yeah, A. So their conditions are a little bit different than the conditions that we used in our textbook, aren't they? If we use A, because ours were sodium borohydride in water. The next one, B, is a Clemmensen reduction, and C is going to reduce the ester 2. And then you have the next one is the Wolff-Kishner reduction. So yeah, I guess the best answer would be A, because it's the mildest reducing agent of all. This one, sodium borohydride, but that's a little bit different than the way it's presented in our textbook. Don't worry about it. There's no way that it's not presented like this in our final exam. So let's move on from there. Number 2, which of these reactions will produce cyclopentanol? So cyclopentanol is this compound here. So if you have a cyclopentane, and then you have a hydroxyl on it. So the first one is reduction of a carboxyl group. But the problem with that is, yeah, you can do the reduction, but you're going to end up with this compound. So you end up with an extra methylene or CH2 group on it. So that's not the correct answer. What about B? Would B work? Yeah, B is totally going to work, isn't it? Right, when you reduce this ketone with hydrogen, you're going to end up with cyclopentanol. And so that would be the correct answer. C is not going to do anything. There's going to be no reaction for this one. And then D is just a hydrogenation reaction where you're just going to hydrogenate the ring down to cyclopentane like this. So the correct answer is B. The next one, we want to convert the ester, the methyl ketone into a carboxylic acid. Did anybody get an answer for number 3? Did anybody try this one? So somebody says potassium permanganate. Somebody else says so we have chromic acid in the first one. Then we have potassium permanganate and potassium hydroxide in the second one. The next one is an iodination reaction, right? What about this reaction? Son of a gun. Sorry about that. Where am I? Oh, here. Yeah. So what about reaction C? Does anybody remember this reaction? Do you remember the haloform reaction? So if we go here, haloform reaction. Right, so the idea is that when you treat the methyl ester, or sorry, the methyl ketone with potassium hydroxide, that you end up with this enolate. Right, so you get this enolate, and then what happens is that's going to react with iodine. So you have I2 like this, and then when you add iodine, you end up with a iodo compound like this, okay, like that. And then what happens is that's going to keep going over and over and over until you make this compound. So you're going to end up with this compound. We have Ci3, right? And this is going to be a good leaving group. And so when you treat that with potassium hydroxide, right, because you're still in potassium hydroxide, the hydroxide is going to be able to come in as a nucleophile like this, and you do a nucleophilic acyl substitution, and then a deprotonation, and then a neutralization, and then that's going to give you the carboxylic acid. So this reaction, we actually call this the iodoform reaction. This is the iodoform reaction. I think this reaction was covered in chapter 20, if I'm not mistaken. So the iodoform reaction. Okay. Question number 4, I'm assuming everybody knows how to do that. So we'll move on to the next one. It says, what is the main product of potassium permanganate oxidation after neutralization? So we have propylbenzene, and then we treat that with KMNO4. Does anybody know the answer to this one? If we take this and oxidize it, where is it going to oxidize? Exactly. It's going to oxidize the benzylic position, isn't it? So that you end up with benzoic acid. That's right, Tiana. That's the correct answer, is benzoic acid. And if you remember, the way our textbook describes it is he says this part of the molecule here kind of goes to compound heaven, right? It just goes in the waste. The way he puts it in the textbook is he says it's excised from the molecule. Okay, kind of a fancy way of putting it, but that's a benzylic oxidation. Good. The next one, I already have the answer written in there. I know you know the answer anyway. If you want to reduce an alkyne to a trans alkene, right, you would use sodium metal reduction. If it says here hydrogen with deactivated palladium, deactivated is the same thing as poisoned, poison catalyst, so that would give you the cis. Anyhow, let's take a look at question number 7. So we're taking this alkene and this ketone, and we want to reduce it. So we want to reduce an alkene and a ketone. So we know that we can't use A because A is going to reduce the ketone. The next one is just aqueous acid, which would form an alcohol, and we don't want to do that. The next one is a hydrogenation. A hydrogenation could work. And then the next one is sodium metal reduction. All right, does anybody know what the best answer for number 7 would be? So I want to compare it to our book. Yeah, I think that's a good guess, Tiana. D is a good guess. Okay, but they're saying that it's not right. They're saying that the best answer, and this is why ACS can be tricky sometimes, it says best suited. So hydrogen with palladium on charcoal. Could you do a sodium metal reduction on this interior alkene? Yes, you can do that, but the only time we ever did that is when we had an alkyne, right? So only an alkyne was used for sodium metal reduction, and so C would be the best choice. And if you're saying, well, Mr. Dion, you taught me that if I took this and hydrogenated it completely, right, that I would end up with this compound, like this, you would reduce the ketone down to the alcohol too. I suppose you could, but it is the best set of conditions would be to use a hydrogenation. It's the only thing in here that could possibly work. Does that make sense to everybody? That why D wouldn't work? Because you'd have to have an alkyne. Cha? Okay, all right. It's kind of a weird question, but sometimes you have to read these carefully and say, does this make the most sense, kind of thing. Let's see here. This next one. So oxidize the hell out of everything. Yeah, okay, well, let's take a quick peek at this one here. So if I am taking this compound, you can see this is a diol. I've got a tertiary alcohol here, and I have a primary alcohol over here. So I'm taking it and I'm treating it with potassium permanganate, which is a strong oxidizing agent, and that would only make a carboxylate. So then I have to neutralize with water and aqueous acid in the second step. Is potassium permanganate going to oxidize a tertiary alcohol? Yes or no? Could you oxidize that? Exactly. So that means that we can cross A and B off of the list, right? C and D are both possibilities. Now the question is, if I take that primary alcohol and I treat it to these strong oxidizing conditions, so KMnO4 is a strong oxidizing agent, which one looks like the best answer, C or D? Heck yeah, it's going to be C, isn't it, right? Because you're going to make the carboxylic acid. Exactly, not an aldehyde, not with potassium permanganate. If you remember, we said that a lot of times we even avoid using potassium permanganate because it's such a strong oxidizer. Okay, let's take a look at this next one here. We've got a few possibilities. We've got the conversion of a ketone to an alkane, if you will. Okay, so the first one is lithium aluminum hydride. That would reduce it to an alcohol. The next one is a Clemmensen reduction. What do you think about a Clemmensen reduction? Would that work in number 9? Somebody says, woohoo, yes, I agree. Yes, Clemmensen reduction is definitely going to be the best choice of action here. The next one, water and acid, that's not really going to do much of anything. And sodium metal reduction, right, that's reserved for an alkyne, converting it to a trans alkene. All right, let's move on to number 10. Which compound can be most easily oxidized? So this, you mix potassium dichromate and sulfuric acid. So this is essentially chromic acid, H2Cr2O. There we go. All right, so we're making chromic acid in situ. In fact, there's only one thing here that can be oxidized. Could anybody tell me which one of these compounds is the only one that could be oxidized? Yeah, it's going to be D, isn't it? Right, because D is an aldehyde, and that could be oxidized further to give you a carboxylic acid. So that could be oxidized to give you this compound, but none of the other ones can be oxidized by chromic acid. All right, number 11. Which product would result from this reaction? I think this is a great question. So we're taking a secondary alcohol and treating it with chromic acid. So potassium dichromate and sulfuric acid, again, that's just going to make chromic acid. So chromic acid. Anybody have an idea about this one? So I'm going to oxidize the secondary alcohol to a ketone. That means it could be either this B, C, or D. But am I going to oxidize that methyl group? No, because it's not on an aromatic ring. Exactly. It has to be C. Right? The only way that the methyl group would be oxidized is if it's aromatic. So this is a cyclohexane. And just, I don't say this a lot in this class because you all know this by now. But remember, an aromatic ring is not the same thing as a cyclohexane, right? These are two completely different things. Okay. All right. I wanted to go over question 12 with you quickly because sometimes the ACS likes to use these things where you have a deuterium atom. And this is actually testing you on a mechanism. So it says, which of these reagents would be best to accomplish this conversion? So you're taking an aldehyde and then you're reducing it down to an alcohol. And so hopefully, if you take a look at these, the first one is D2O in acid. That's not going to do it. Deuterium peroxide in acetic acid, no. Then you've got sodium deuteroxide in deuterated ethanol. That's got nothing to do with it, right? But if you look at the next one, instead of sodium borohydride, it's sodium borodeuteride. And so what you would have is the borodeuteride ion, which would look like this. You just replace the hydrogens with deuteriums like this. And so the first step of the mechanism is going to be this. And that explains why we have a deuterium in this position. And then once you've made this intermediate, so you get this intermediate, which is going to look like this. You have one deuterium and one hydrogen. In the second step, you treat it with water, right, in aqueous workup, and that's going to put the proton on here to give you the neutral compound like this. All right. Number 13, I have the answer on there. Number 14, we didn't cover that one. So let's take a look at some of these questions down here. I think that this one was on the practice exam, or the practice quiz rather. Number 1, which ketone is going to absorb at the lowest frequency in the infrared? So we have 3 ketones. Could anybody identify which one is going to absorb at the lowest frequency? It's not going to be A. So if you take a look at these, if you remember, when we looked at wave number in organic chemistry 1, so wave number was equal to 1 over 2 pi times the speed of light multiplied by the square root of the force constant divided by the reduced mass. And so we see that wave number is directly proportional to force constant, or at least the square root of the force constant in a way. And so, you know, which one's going to have the lowest absorbance is the one that's going to have the weakest carbonyl bond. And the one that's going to have the weakest carbonyl bond is going to be this one. It's going to be B, because that one, the double bond, is conjugated, right? So conjugated, we'll put here conjugated carbonyl, therefore weakest. It's going to be the weakest carbon-oxygen double bond stretch. Okay, let's practice another one here. Number 2, which compound is consistent with the IR? Could anybody identify any of the functional groups in number 2? Yeah, there's definitely an alcohol, isn't there? We have the oxygen-hydrogen stretch at around 3,200 to 3,600, something like that. So the only possibility would be C, because it's the only one that's an alcohol. Okay, what about number 3? Number 3, it says, which is the most reasonable structure for a compound with this IR spectrum? We can see I've already done some of the work on here to begin with. It's definitely not an alcohol. So we'll put here not an alcohol. So that's why we can scratch this one off. It's also not a terminal alkyne because there's no CH stretch at 3,300 reciprocal centimeters. So that's why we can cross this one off. But you notice that we have a stretch here, right? We have a stretch here around what, 2150 to 2100. And so this would be a carbon-carbon triple bond stretch, right? So we do have a triple bond in there. And then we also have a carbon-oxygen double bond stretch from an ester and a carbon-oxygen single bond stretch from an ester. So we have this functional group and we have this functional group, and therefore the answer must be A. If you remember in the IR, one of the most recognizable functional groups outside of an alcohol and a carboxylic acid is an ester, because it's the only functional group where you have such a strong carbon-oxygen single bond stretch. You can see this is the strongest absorbance in the entire IR spectrum. So that means that we have an ester. Number 4. Does anybody recognize any functional groups in number 4? I'm sure you do. Yeah, it's a carboxylic acid, isn't it, right? This is the oxygen-hydrogen stretch of a carboxylic acid. And so the only one that's a carboxylic acid is B. So that seems reasonable to me. And you also have the carbonyl stretch here, or you have the carbon-oxygen stretch there. Okay, let's move on from there. Number 5, which structure is the most consistent with this infrared spectrum? So here we have some absorbances, that are pretty high, and there's 2 of them. They're kind of weak. So what kind of functional group do we have if we have 2 stretches up here around, up here around 3,400, something like that? It's a primary amine, isn't it? Right? Because you have RNH2 like that. So that means it could be this compound, or this. So we can scratch C off of there. Why can we scratch A off of there? Could anybody tell me why we could scratch A off of there? Right, we can scratch A off of there because the compound is aromatic. Right, you can see here you have the carbon-carbon double bond, aromatic stretching like that. So now it means it's either B or D. So could anybody tell me which one of these it is? Is it B, is it aniline, or is it D, paramethyl aniline? So there's one more stretch in here that we don't talk about a ton. What does it mean if we have a bunch of stretching below 3,000? That means that we have some sp3 hybridized carbon-hydrogen stretching. And we don't have that in B, but we do have it in D, right? We have those carbon-hydrogen stretches from an sp3 hybridized carbon. Isn't that neat, though? It's a neat problem, kind of some process of elimination to solve that one. Yeah, it's a good problem. Let's take a look at, let's try number 6. So number 6, which compound corresponds to this IR spectrum? Sometimes we like to do this, like to draw a line around 3,000, something like this. So I get a line that looks like that. And then maybe another one around, I don't know, 1,500, 1,700, something like that. I don't know, maybe 1,500. Something like this. All right. So you notice that we have a stretch here right above 3,000. Does anybody know what this one represents? So if we have something just above 3,000, so that's sp2 hybridized carbon-hydrogen stretching. So that suggests that we might have an alkene. So it could be, it could be this. In fact, it's the only possibility. So it's the only one with sp2 hybridized carbon-hydrogen stretching in it. Yeah. So it's an alkene. Yeah, it's a carbon-hydrogen stretch that's vinylic. Yeah. All right. Also, you notice that in this one, we have a stretch here at 1630. So this is at 1630. This is the carbon-carbon double bond stretch of an alkene, not aromatic, but an alkene. All right, so the answer has to be A. Okay, let's move on to number 7. 7 is a good question. Let's try this thing again where we draw a line at around 3,000. Something like this. So draw a line around here. If we draw another line around 1,500 or something like that. Yeah, it's going to be A, isn't it? Why is that, Audrey? You're right. A. So it can't be a carboxylic acid, right? Right, because carboxylic acid would have a big stretch up here. So it's because of these 2 signals right here. So these are usually around 20, what would they be? Around 2750 and 2850, something like that. Usually around 2750 and 2850. So that's an aldehyde. So this is an aldehydic carbon-hydrogen stretch. Yeah, there you go. Then you're right. We have the aromatic overtones here. We have the carbon-carbon double bond stretching from the aromatic ring. So we'll put CC double bond, aromatic. Yeah, that looks reasonable. Number 8. Now, this is a good question. It says, which is the correct order from lowest to highest field for chemical shifts predicted? So which one of these, I'll just ask you this way. Which one of these is going to be the most deshielded? Would it be 1, 2, or 3? Yeah, 1 by far, right? So 1 is going to be the most deshielded. So we're going from lowest to highest field. So highest field is going to be the least deshielded, and lowest field is going to be the most deshielded. So the one that's the most deshielded is going to be number 1, and it's going from lowest to highest. So the answer kind of eliminates it pretty quickly, but it has to be C, right? So if you're going from 1 to 2 to 3, that makes sense that you're going from low field to high field. Yes, so that makes sense. So lowest field, we'll put here from lowest is going to be most deshielded. So we'll put here most deshielded. All right, something like that. I think we already covered this question before, so I'm going to skip that one. Oops, this one here. And then this one here, I think I did some of this too. Let's try number 10, because this kind of thing shows up on MCAT sometimes. Question number 10. Which proton NMR spectrum is consistent with ethyl methyl sulfide? So the first one, we have a triplet that integrates for 2 protons. Then we have a single that integrates for 3, and a quartet that integrates for 3 protons. So first, let's talk about what's the multiplicity of everything in here. So if we go CH3, and then we go CH2, and then we go sulfur, and then we go CH3 like this. So the methyl group that's in black, what would the multiplicity be for the methyl group in black? Will that be a singlet, doublet, triplet, quartet? It's going to be a triplet, right? So thanks, Audrey. We've got a triplet for this one. What about the 2 protons in red? What are they going to give you? Quartet. Yeah. So we get a quartet for this guy. So we'll put here quartet. And then the 3 in blue, that's going to give you a singlet. So we should have a triplet, quartet, and a singlet. What do you know? All 3 of them have a triplet, quartet, and a singlet. But the quartet should integrate for 2 protons. And you see that in the first one, the quartet, 2 protons are a triplet, so that's impossible. If you go to B, B is a possibility. The same thing, yeah, the quartet is integrating for 3 protons, so that's impossible. For sugar. No, the quartet is integrating for 3 protons. Sorry, what am I doing wrong here? No, A is possible, isn't it? Sorry, Mr. Dion can't see. So you have 2 protons that give you a quartet. No. So this is not possible. A is not possible. 2 protons giving you a quartet in B, that's possible. 2 protons giving you a quartet, no. And 2 protons giving you a quartet. So it's between B and D are the 2 possibilities, B and D. Now, if I look at this, one of them has a singlet That's a little bit above 2, and the other one has a singlet a little bit above 2, so I can't use that. But which one of these looks the most reasonable? So you see they both have a quartet that integrates for 2 protons in B and D. But if you look at B, the quartet that integrates for 2 protons has a higher chemical shift, right? Which makes sense because it's next to a sulfur, right? So it should be the most deshielded. And so the answer would be B. Give me a thumbs up if you follow me on that one. Right, so this is the methylene in red here. This is the methyl group in blue, right? It's deshielded because it's attached to the sulfur. And then we have the methyl group in black here. All righty, good. Number 11, I think this is another question I asked in that quiz maybe. How many signals would you see in the carbon-13 spectrum of this compound? So there's a total of, let's see, let's count them. 1, 2, 3, 4, 5, 6, 7, 8 carbons in the molecule. But does anybody have an idea how many signals you would see? So if we look at these 3 protons, yep, those are all chemically equivalent, aren't they? Right, this one is unique, this one is unique, this one is unique, this one is unique, and then this one is unique. So we have a total of 1, 2, I don't know why I highlighted those 2 in green next to each other. That makes no sense, Mr. Dion. Would have made way more sense if you had done something like this. There we go. So we have a total of 1, 2, 3, 4, 5, 6 signals for this guy. All right, because remember, you have free rotation around this carbon-carbon bond here. And so those 3 methyl groups that I have highlighted in yellow, those are all chemically equivalent, and none of the other carbons are chemically equivalent in any way. All right, number 12. Which structure is consistent with this proton NMR spectrum? So if I have a proton with a chemical shift of 10, does anybody know what functional group that means? Functional group do we have? No, not a carboxyl. It would be an aldehyde. All right, so this means that we have an aldehyde. Good, so that means it's going to be either this compound or this compound. We can scratch these ones off. All right, then you see that we have a triplet in a quartet. Well, here, this would give you a triplet, this would give you a quartet. And in here, this would give you a triplet, and this would give you a quartet. And so what else do we have? We have these 2 peaks here around 7 ppm. What do we know when we have signals like these in the green circle? When you have a doublet of doublets that are kind of tilted in towards each other like this, does anybody remember what that means? It means you have a 1,4 substituted ring, don't you? You have something like this, right? So you have an X and a Y over here, right? We call that para substitution. There you go. Yeah, para substitution. And so the answer is going to be C, right? Because C is the only one that has para substitution. Can't be A because A is only mono substituted. Good. All right. Question 13 is kind of an interesting problem. If you count the multiplicity here, you've got, I mean, if you look really close, this is 1, 2, 3, 4, 5, 6, 7, 8, 9. So what would you call this? A nonette? Honestly, you guys, I've never even heard of a nonette before, but you could call it that. Anyhow, maybe. But we have 6 protons that give you a doublet. So these are 6 protons, and this is a doublet. Then you have 2 protons that give you a doublet over here. Then you have 1 proton that gives you a singlet. Well, if you have 1 proton that gives you a singlet, you notice that all of these are alcohols. And so for each one of these, this proton is going to be the alcohol proton. Okay? It's going to be the alcohol proton. The reason the answer can't be A is because A is just going to give you 1 big singlet because it's terbutanol. If we look at the next one is impossible because you should see a triplet, right? This would give you a triplet, and this would give you a triplet. So there's no triplets in there. So let's take a look at C. So if we look at C, let me just draw the bond line structure like this, maybe something like this. So then we have, there we go. So this hydroxyl is going to give you a singlet. These 6 protons are going to give you a doublet. So far it's looking good. And then this methylene here, that's going to give you a doublet as well. So far that's looking good. And then you have this 1 proton here. But this 1 proton is coupled next to 1, 2, 3, 4, 5, 6, 7, 8. So if you take 8 plus 1, that gives you 9. So that would give you the nonette, this thing here, right? So that means that C must be the correct answer. If we look at D, the problem with D is that if you draw the bond line structure of it, so it's going to look like this, so just 2-butanol, this is going to give us a triplet. This is going to give us a doublet. This methylene here, so it's coupled next to 1, 2, 3. So this is going to give you a quintet, and there's no quintet. And then this one here is coupled next to 1, 2, 3, 4, 5. So that's going to give you a sextet, and there's no sextet in there either. And so C must be the correct answer for that one. If we look at question number 14, it says, which structure is consistent with this proton NMR spectrum? You notice that everything in here is a singlet, 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 singlet. And if you look at all of these, I mean, all of these protons here would give you a singlet. These would give you a singlet, and this would give you a singlet. These ones here maybe would give you a singlet, yes, maybe, but this would give you a quartet, and this would give you a triplet, so this can't be right. This would give you a quartet, and this would give you a triplet, so this can't be right. This would give you a singlet. This would give you a singlet. This would probably give you a doublet of doublets, wouldn't it, Audrey? You'd probably get the doublet of doublets for this one. But if we look at A, it doesn't seem unreasonable that it could be this compound. So let's just review why it's possible that this could be the correct answer. So we'll put singlet here, put singlet here, and then we'll put singlet here. So we'll color code these. So if we think about the chemical shift of these 3 protons here, we start with a baseline of 0.9 and we add 1, which gives us 1.9 ppm. And you can see that that singlet at the lowest field is around, close to 2. So that looks pretty reasonable. If we look at the methylene, so these 2 here, we start with the baseline of 1.2, and they're next to the oxygen of an ester. So we're going to add 3 for that. And so that's going to give us 4.2. But also keep in mind that it's attached to an aromatic ring. And so it's actually going to be higher than that. So it's going to be greater than 4.2 ppm. And yes, this signal is greater than 4.2. And then you have all the other ones here, and these are going to be aromatic. So aromatic. And so that looks the most reasonable. Let's just cover number 16 quickly because I want to go over the whole idea of a proton coupled spectrum. So usually we do decoupled spectrum in the carbon-13, but you can have a coupled spectrum. And so if it says quartet or if it says Q, what that means is a quartet. So that means that this carbon is a methyl group. It's attached to 3 hydrogens. So this one is a CH3. And then if it's a triplet, that means it's attached to 2 hydrogens. So that would be a CH2. And then, of course, if it's a doublet, it's a methine because it's only attached to 1 hydrogen. So we're looking for 2 methyl groups, a methylene and a methine. And if we look at the first compound, compound A, sorry, let me delete that. There we go. If we look at compound A, we see that we have, 2 carbons that are attached to oxygen. Well, the problem with that is that none of them we don't see any CH2s and CH3s above 50. And we know that if you have a carbon that's attached to oxygen, that's going to show up between 50 and 100 parts per million. So that means we have to have a methine attached to oxygen. Well, we don't have it in this compound, and we don't have it here either. We don't have it in this compound, but in this one, we do have it, don't we? We have the methine that's attached to an oxygen. We have two methyl groups, right? And then we have a methylene. There we go. And that seems to make the most sense by far out of any of these compounds. Okay.